So we're going to talk about distributed computing on large commodity clusters with Apache Spark. I'm Reza Zadeh. I'm a professor consulting professor at Stanford and a technical advisor at Databricks, the company behind Spark. So let's dive right in. I'm going to start with a very quick overview of data flow programming versus traditional network programming. Then we'll, again, very quickly introduce MapReduce and why it's successful. Then we'll move on to actually introducing Spark, its core components. Then we'll use Spark. We'll see what's currently available in the Spark package that you can download today. So I'm a computational mathematician, so what you're going to see is more on the side of actually using Spark for machine learning, for numerical linear algebra, for algebra, and for scientific computing. I can speak with you. We'll also go into the system side of things, but less so. And then we'll also go into what you can expect to get when you download Spark in, say, 2 to 3 months from now. So ongoing work that's currently being shipped into mass. So we all know there's a ton of data in the world, and for the past 2 decades or so, it's become very, very common to, instead of buying very expensive supercomputers, to tie together a lot of commodity machines. And by doing so, you hope that you would get the same bang per buck with the total amount of resources available across your cluster as you would get if you had bought a really expensive single machine. So the single machines become much more expensive than tying together a lot of machines. This is why a lot of people do it. So then you need to figure out how to actually get these computers to talk to each other. The major problem is that they have to speak over a network. You don't have high performance connections between the computers. So you have to get them to coordinate. And there are a lot of distributed computing paradigms and frameworks, and they've been flourishing for the past few decades. The most traditional one is MPIs, simply have message passing at an arbitrary level between machines. And so you're responsible for all the communication. As a programmer, you're responsible for all the communication between the machines. So this is very difficult to actually pull off successfully for several reasons. One is, how would you deal with a machine going down? You usually have to restart your whole computation. And then how do you make sure that a relevant part of your data that is on a machine is handled locally? So if your problem is, say, embarrassingly parallel, you should be able to do the embarrassingly parallel part that's on one machine on that machine without shuffling it around. So you would have to care how your data is split around the cluster as well. And then there are much more hairy problems, like what if some computer gets overloaded because you didn't think your algorithms through, and then you can't have too much communication too. You don't want to deal with that. It's a lot of hassle, and we're used to programming really nicely on a single computer. You have RAM, you have disk. Don't want to deal with that. Okay, so it's actually, MPI is rarely used, even in the scientific computing world. People are moving away from it, even though they need to get as close to the metal as possible. They still prefer some sort of cluster management and some sort of data flow so that they don't have to deal with all of these problems. So this is where data flow comes in. Data flow models come in. They restrict what you can do. You can't just do arbitrary message passing. You can't do all-to-all communication. Well, you can. You can still shoot yourself in the foot with these frameworks, but they try and help you so that you don't. The biggest example of these data flow models is MapReduce. I bet most of you are familiar with it, so we won't go into too much detail. But basically, MapReduce gives you distributed file system, gives you data locality to your computation, gives you fault recovery, so if part of your computation dies, it's recomputed automatically. And it does all this at one cost. You have to give it the promise that your data and your algorithm can be processed by simple maps and reduces. So it's all you have at your disposal. The MapReduce contract is that your data is going to be read in. Pairs will be spit out by mappers. Pairs, keys and values. And then there's just one promise given to you. That one promise is that the pairs that have the same key show up on the same machine. And then you reduce on those. That's it. And so that, in its own, has been tremendously successful A lot of Google's early success was based off of it. Much of the companies that you guys are working at probably use it. Many of the companies you guys are working at probably use it, and it's still very successful, and is slowly going away. Why? And you'll see why. So it's been successful for a very good reason. So you can do a hell of a lot in it. You can do matrix vector multiplications. You can do power iterations. For example, PageRank, Google's first version was implemented there. They did crawling with it. You can do machine learning with MapReduce, albeit a little bit slow. The Mahout library lets you do this. Although they're now slowly moving away from MapReduce. Not slowly, actually quite abruptly. They suddenly decided that we're not going to take any more MapReduce submissions to Mahout, and it's being switched to Spark. So other things you can do is some modified version of SVD. So if you're willing to flip coins and accept some error in your singular value decompositions, you can do that on MapReduce. And tall and skinny operations on matrices such as QR and SVD are possible on MapReduce without too many passes. So even though you might think of these as needing iterations, people have thought of how to shoehorn SVD and other algorithms into MapReduce so that you don't need too many iterations. Yes?
Quickly elaborate on acronyms SVD and QR.
SVD is the singular value decomposition. It's a matrix factorization. It's very commonly used by the data science community in recommender systems and by the scientific computing community in solving and analyzing PDEs, partial differential equations. And QR is not an acronym. It's a decomposition of the form Q and R. A matrix, you decompose it into a unitary matrix Q and a triangular matrix R. Okay. So why would you use this? Because, well, it's a lot easier to use than MPI. It's higher level, so you lose it's higher level, so you have to think a little bit less about all the little details. And the largest clusters use this. Now, already people realize that, okay, MapReduce is not doing enough for me. I don't want to write a mapper and a reducer for every little algorithm. So there are higher level languages on top of MapReduce, such as Pig. So Pig will take roughly, vaguely SQL-looking like syntax and turn it into MapReduce code for you. So you run a Pig script that's maybe 20 lines long, and it gets turned into maybe 30 MapReduces, and they get shipped off to your cluster, and the results come back. That's pretty nice, but you did actually run 30 MapReduces, and you pay the cost of 30 MapReduces. Same with Hive. Hive does this, and so these two are very similar. Scalding will take Scala code and do that for you. Turns it into MapReduce. Storm is slightly different. It's a data flow programming model that is more general. There's inputs, there's outputs, and a general DAG of how data can flow. So there are a lot of these. There are some others that are less popular, and they're not being named because I would say that there's some kind of a battle going on between these to win the hearts and minds of data scientists, basically, so that there should be eventually only a few really popular tools in this space, I would say. So what are the limitations of MapReduce, which is currently the most popular of these tools? So it's wonderful at one pass over your data. So if you just want to read your data, do something, say count some numbers, and then you only ever want to do that once a day or so, it's pretty good at that. But if you want to go over your data many times, which very often you do, for example, machine learning, for example, if you want to query interactively, if you have some logs that need to be constantly queried, and if you don't have any communication between successive MapReduce jobs, then MapReduce is great for you. But if you want communication between successive MapReduce jobs, you either have to set up a distributed hash table, so you have to get Cassandra going, or some other way to have your mappers communicate with each other and have the subsequent MapReduce jobs have access to data from before, or you write to disk, you read from disk, which we all know is not very fast, especially since the disk here is it's replicated HDFS disk, so there's more work than a regular disk read that every time you read and write. Okay, so just so that we see this clearly, we'll focus on 2 examples, and there'll be more, but 2 examples where MapReduce is not the best thing in the world. If you have iterations, you're going to have to read all the data, which takes quite a bit of time when you're going from disk, and do your first iteration, write it again, read it again, do something, write again, read again, etc. So you want to avoid that. And also if you have queries, so you have some logs, you've got a bunch of errors, and then you want to see whether they are. You don't want to rerun over all your data and read from disk, write from disk every time you come up with some new error that you want to look for. So an example of an iterative task that MapReduce was initially used for and is still pretty decent at is PageRank. So you have 2 data sets. One is the data sets of edges in the graph, which is the web, i.e. neighbors. So you have the ID of the node you're at and its outgoing edges, and then you have the current guess for the PageRank vector. And every iteration is a power iteration, so you're actually trying to find the eigenvector of a matrix. And every single iteration has 2 MapReduce jobs involved. The first MapReduce job would simply take the current guess for the PageRank vector and distribute it across the neighbors. The reducer would sum up these contributions, and then you'd have a new guess for the PageRank vector. However, you now need to take this new guess and decorate the neighbors. You decorate the graph with the new guess for the PageRank vector. So that needs another MapReduce. So every iteration needs to do the actual matrix multiply, and then the matrix multiply also. Then there's another step to just put the resulting matrix vector multiply next to the next iteration. So you'll see, it's actually not necessary to have these 2 MapReduces if you had control over the partitioning. If you knew that your data is going to a particular node, you wouldn't have had to do this second MapReduce. And furthermore, you wouldn't have had to, if you knew that your data is going to be used over and over again, you wouldn't write it out to disk and then read it off disk again. You just keep it there. So that's something that MapReduce won't let you do right now, but you'll be able to easily do with Spark. So that's what I mean when I say there's a lot more communication cost and in MapReduce. Okay, so let's begin introducing Spark, and we'll go through it not that quickly because I hope that this is relevant to the audience. By far, the most important part of Spark is the resilient distributed data set. So all the code in the Spark database, in the Spark code base, follows camel casing, which means the first letter should be, the first letter of a class should be uppercase and then lowercase thereafter. But for RDDs, we make an exception because they are so important. So the RDD is the base layer of Spark. So you're all familiar with programming with collections. So any programming language you use, be it Python, be it C++, provides you with some collection environment, a vector, so that you can put data into a collection and deal with it however you like. A vector or a dictionary, all programming languages have this. Wouldn't it be nice if there was such a collection that was distributed? That's what a resilient distributed data set is, an RDD. Of course, it can't provide you with all the things that a regular vector in C++ has. That'd be asking for too much. But it provides as much as it can. Of course, one of them is map, one of them is reduce. So you can very easily do a MapReduce on your RDD. But you can do a hell of a lot more. And it's almost at a point where it's not healthy to think about MapReduce anymore when you're trying to design your algorithm. Previously, you had to shoehorn your algorithm into maps and reduces. Now that you have so much power at your disposal, it's not really healthy to think about maps and reduces, even though you can. Okay, so the project is actually very, very active right now. I'll go more into numbers after, but we currently have more than 50 companies contributing code, and the APIs are available in Java, Scala, and Python. So all of these are available. Yes?
So I just wanted to be clear. MapReduce is or Spark is a proper superset of MapReduce, so you don't have to start over from scratch.
Yes, absolutely.
Okay.
Yeah. But it's actually not worth thinking about it that way anymore. It's like when you design your algorithm, it's better to think about, okay, what are the transformations I have at my disposal? What's the algorithm I want to do? go and learn the new transformations. Don't think about maps and reduces as if they are necessary and as if that's the only benefit. As if the only benefit you'll get is being able to do maps and reduces faster. It's not that. You have a lot more power. So Scala is what we develop in, and then we have bindings for Java and Python, and they're pretty clean API. So even though I said it's a distributed collection, it's available in several languages other than Scala. So yes.
If people use Python, do they gain the same power as using Scala?
Yes.
Can you repeat the questions for the video? And
Oh, if you use Python, do you gain the same power as you do with Scala? Yes, you do. We add in Python and Java bindings as soon as we can after we have the Scala code. So we usually develop the operations natively in Scala, and then as soon as hopefully in the same release, so that you don't even see the development going on, we add in Python and Java bindings. Maybe I should. Yeah, okay, one more question, and then please keep questions so that we can have them towards the end. But I'll take it.
I understand that there is also binding for R.
Yes, so that's more of a research project. But yes, people have taken.
Question?
Oh yes, sorry, I gotta remember that. There's a question about whether you can use Python, you can use Spark from R, and the answer is yes. There's a Spark R project, and it's more of a research project right now, but it does work. You can productively use it. I just didn't put it in this list because I wanted to write clean APIs. It's in R right now. It's a little so it's pretty nice. I would use it.
I've used it.
There we go. So we have a Spark R user who likes it, and I like it as well. But I wanted to yeah. So yeah, you have R bindings as well. All right. So let's take a look at what a few RDD operations look like. So we can simply read an RDD from disk. So this is a MapReduce, by the way. This is a traditional word count example. And so you can simply read an RDD as a text file sitting on HDFS. You map it to the words, so it's just assuming there's a word per line. You map the word to one, and then you reduce by key, which is the regular reduce operation summation. And then you want only that's it. So these two lines give you MapReduce, as opposed to the Java regular MapReduce that needs a lot more. So this is comparable to the amount of code you'd have to write in Pig, or one of the other high-level languages that we talked about. And then we can filter by only the ones that have count greater than 10. So only the words that have count greater than 10 show up. And now this isn't going to start another MapReduce job, although even Pig and Hive and so on, their compilers are optimized enough that they would shove this filter into the reduce. But in general, if you'd been naive about this set of operations, you would have taken the filter and run a new MapReduce job for it. But of course, that doesn't happen. We don't. We simply do the reduce. We know how the RDD is partitioned, so we just tell those nodes, okay, now filter. And then the filter happens. And then we want to do some this happens to be a small set, so let's say we want to put it in memory and actually then join it with another big data set that we can read in later. So that's what we'll do. We'll put it in memory. Cache puts it in memory. We'll filter for those that are about news, and then we can join with another RDD. And this is all. Join is an example of an operation you can do. Everything I show you, the blue is going to be Spark operations, and I guess it looks pink, is Python. It's regular Python. Okay. So the key idea is that RDDs know how to rebuild themselves, and they also know about where they're being partitioned. So they know where in the cluster they're being stored, so that if there's an operation that can be subsequently done on the same partition, or by keeping the data in memory and then operating on it there, that will happen. Okay. So how do they know? Okay, so there's another example is iterative querying. So now you want to keep your data in memory so you have a shell at your disposal, by the way. So when you want to run Spark in an interactive mode, you simply start up a shell like Scala or Python, and then you type in your commands and they get shipped off to a cluster and you get results back. So if you're, it's 2 a.m. and your site's crashed, you want to look at the logs to see what went wrong so you can fix. You want to run many greps over all of your logs, and the logs are 100 gigs. They would fit across your entire cluster if your cluster's memory. I'll get back to your cluster's memory if you could do it, and of course you can. So what you do is you load up your messages, your error messages, and you put them in. You cache them, which means you're now going to put them in the memory and keep them there, and you start desperately looking for where the error is. And you can run many of these searches so that each one does not produce a MapReduce job, and each one keeps the data in memory, and the results come back to you way faster than if you had to read and write from disk and start off a new MapReduce job. Question?
So does the cache work like sort of like shared memory, meaning does it live across Spark jobs?
No. Cache means that whatever part of the RDD is on a particular node gets put into memory, so that if that part of that is being touched by the local machine, it's in memory. It's not suddenly providing you with a distributed hash table. It's not the case that you can suddenly, on one machine, go and read what's in memory on another machine easily or without the cost of the communication. You can't. That's asking for too much. It's not a distributed memory. You can't think of it as distributed memory suddenly. But you can think of the RDEs of nodes that can handle their data locally as keeping their data in memory and handling them in memory locally. So how do RDEs know how to build themselves if they fail? So let's say you're doing some iterative job, and on the 5th iteration, node number 5 dies. Well, an RDD actually keeps track of how it was built. So the world lets you build RDDs in all kinds of ways, but all of those ways force the lineage of the RDD's creation to be tracked. So when this file initially came from HDFS, but we had to read it from Spark context.hdf text file, and that created the first version of the RDD, so we know where it came from. And then the MapReduce filter, these are all implemented by us, and so we know what you did to get to the RDD that you're at. And so if there's ever a failure, let's say this node failed, we know how to recreate it. So that's how it's done. If there's a failure, the recreation is because we know how the data was created. And so you don't need to worry about this. Now, partitioning as well. We know, an RDD knows where it's being put, how it's being partitioned across clusters, so that if there's a filter operation after reduce, it knows that do the filter right after the reduce on the same node, because there's no need for filters to communicate with other nodes. So that's basically an RDD. Any questions about RDDs? Yes?
What kind of transaction manager do these things have? Does it have a zookeeper in case the master dies? Like, how does it vote master?
So if the master dies, I believe a new master is rebuilt. But then that's actually a question that I'm not certain of that answer.
Okay.
Yeah, so I'm not sure how master is kept up to date. But your cluster manager should start a new master.
That's usually handled by the transaction manager. So it depends on what kind of transaction manager the system uses. I'm not sure what transaction manager you use.
So Spark will run on top of Mesos and on top of Yarn, and also in standalone mode. So if it's on Mesos, I believe Mesos will restart it, but I'm not certain about that. And if it's on Yarn, Yarn. Okay.
Mesos will restart.
There we go. Mesos will restart. Yes, question.
So you talked about the lineage, right? Who keeps track of the lineage?
Spark does.
Question?
I forgot the last question. The last question was, what happens if master dies? Who recovers it? And the answer was the cluster manager, being Mesos or Yarn. And the other question was, who keeps track of the lineage? Object-oriented programming does. I mean, so what happens is we, as creators of Spark, do this by keeping track. Like every time an RDD is created, it's created by calling methods on another RDD or from some sources that that originate it all, and then so we know that this RDD is derived from this one because of inheritance. Actually, so one RDD will know that it's deriving from another RDD and so on. Yes.
Have you enabled encryption at rest or in motion with any of your infrastructure yet?
Have we enabled encryption? What was
At
it?
rest or in motion? So encrypting in memory or any network communication?
No. That's network communication. I don't think so. I don't think so. But we're very open to contributions. So if you're willing to, so I haven't heard of this request too often. But I mean, when you write to HDFS, there's nothing stopping you from writing your own encryption, so that if the data is sitting on disk, only you can read it. But while it's in memory, I don't think we can give that promise right now. Okay? Yes, question.
So you mentioned that RDD is for containing collections. And what kind of data structures in the collections can be there, like three-dimensional arrays or?
Oh, arbitrary. So as long as you're not. So this is one of the cases where you can't shoot yourself in the foot. So whenever you put stuff into an RDD, one item of it should fit on a single machine. Okay, so RDDs are typed. So you can make an RDD of an array. And in fact, how we store a matrix, for example, is an RDD of an array. And that array is going to be rows of the matrix. So these rows are non-trivial. I mean, they might have, say, 1 million, 2 million, maybe 10 million, maybe even more, as long as it can hold on a single machine. So that's the answer to the question. Arbitrary. However, don't shoot yourself in the foot. Don't put too much in a single item of an RDD. We have all kinds of examples. The matrix example is an interesting one because sometimes the matrix's row is too much, and for those cases we have sparse matrices. So you can make an RDD of a vector that is indices to entries, and then that will let you handle larger matrices that are sparse.
Do you use sparse matrices for three-dimensional arrays as well?
Sure, yeah. That we don't have three-dimensional matrices right now, i.e. tensors, but there's nothing stopping you from handling it yourself via RDDs of arrays of 3.
It's a basic question.
Sure.
I missed part of your early slides, but I read somewhere it is RDDs are immutable, and that
yes,
essentially says that
the question is, are RDDs immutable? Yes, they are.
You're only looking at coarse-grained data, which is not very fine. So my question is, the Sharp help with looking at more
Sharp?
Yes, Sharp or Storm or other.
Okay. So the question is, RDDs are immutable. Are RDDs immutable? The answer is yes. Now, to follow up, I'll get to the second part of the question in a second. The RDDs are immutable. However, when you look at a sequence of operations like this, it's not the case that an RDD is materialized for this, and an RDD is... That's strange. Oh, my sleep. So it's not the case that as you're creating an RDD, you have intermediary RDDs being created. That's not what's happening. You only get computation happening when you do something that needs an output. So actually this, if you ran this, nothing would happen. Only when you did something that needed an output from the RDD, like a count, or if you wanted the first element, then all this stuff, all the lineage gets compressed and optimized to the point where one computation and then ran in as an efficient way as possible. Okay? So immutability is not really an issue, but more so a help to make the code look nicer. Now, with regard to the second part of the question was, can Shark help with the fact that... So I didn't understand why you said that Spark is more so for coarse grained data versus fine grained. You can get as fine as you like with RDDs. You can just put RDDs of integers, and that's not a problem. Now, Hive can be ran, instead of having Hive run MapReduce jobs for you, there's a project called Shark that runs the Hive code that you might be familiar with on a MapReduce engine so that you get the benefits. But then you're restricted to SQL. So I don't like that. I don't like being restricted to SQL. I'd rather have a full programming language at my disposal. But there's a very good place for SQL in the world. You know, it turns out that SQL is incredibly nice and useful for people. So we support that.
So just a second, also very basic question. What's the difference between Hive and Shark?
Hopefully none, but there are differences in that the version of Hive that Shark supports is slightly different from master. But other than that, you know, we try and keep it as good as. Let me. Okay, last question for this part, and then I can ask questions in the later part. Yes.
Some time ago you mentioned that each element of the collection must be on one node. So what if the element itself is a list? Does it resolve down to the lowest leaf of the tree where the atomic elements of the children's list would actually be there? Or are we restricting the entire list, which it happens to be an element now, to be on a single node?
So, do I need to repeat the question with the microphone? No. Okay. So the question is, what if you have too large of an element in an RDD? You will spill the disk in the same way the MapReduce does. But it's just bad programming practice to do this. So you want to chop up your data as much as possible so that you don't resort to spilling the disk.
Right, but if each element itself is a list.
So yeah, but it's a regular Scala or whatever you have you list.
Right.
That doesn't fit in memory.
Yes.
Then you'll spill the disk.
Okay.
So you mean to say there's no concept of virtual memory, and therefore you must limit your RDD design to real RAM on one node?
For a single entry in an RDD, you should try and keep that single entry small as not too large. Like, so when you build vectors, right? In any programming language, you're on a single machine. When you build a vector, you don't shove an item that doesn't fit on a single. You don't expect to be able to build a vector of elements where a single element is already forcing you to crash the disk, right? So why would you expect that to suddenly? So if you have a lot of these items, you'll get partitioning across the cluster, and if you happen to have so much of these items that even the total amount of RAM in your cluster that can't handle all of it, you'll use disk. But you should try and at least, this will be mitigated if you chop up the entries in your RDD such that a single element of the RDD is not too much. Okay? So let's move on to numerical computing. So now we know the basic components that Spark provides, and we're going to use them to do some non-trivial things. The first thing we can do is machine learning. So an example of logistic regression in Spark is entirely in this slide. So we read in our data points. We generate the current guess for the weights, and then we do these iterations, which we had trouble with before. And every time we update, so these are all the possible. These are all every single in logistic regression. Every point contributes a loss, and what we'd like to do with gradient descent is subtract the gradient of every single point from the current guess for the weight vector. So we're computing that here. This part is Python code that computes the derivative of the loss, logistic regression loss, for a single entry given the current guess for weights, which is W. So this happens. So we have now the gradient entirely, and then we reduce it to sum up the contributions from all the data points, and then we subtract that from the gradient. That's gradient descent, and it's logistic regression. That's it. You can do so now. If you had another fancy loss here, another fancy update, like you could update for SVMs. You could update for even k-means or some other fancy update. You can do it. You can do a lot of different optimization algorithms as long as the loss is separable, which it is, and very often in machine learning, in fact, very often in machine learning, the loss is separable, and this lets you handle those cases very nicely. The data will stay in memory as long as it fits in memory. If not, you'll keep it on the same node. You won't write the whole thing to disk and read the whole thing again. Okay? So that's what's getting you these gains. Now, if you run Hadoop with the same code pretty much, you do much worse than Spark. I mean, this is it's pretty clear. The gains go all over the place, but ballpark numbers are from 10 to 100 times faster than MapReduce. So PageRank is another example. For PageRank, remember we had 2 MapReduces per iteration, one to just spread the PageRank current guess for the PageRank vector across the nodes, and then another to decorate the new guess for the PageRank on the graph. In that case, in this case, we don't need to do the second MapReduce, which was we can just keep telling the map that's responsible for distributing the guess for the PageRank to the nodes that will have the next guess there. So this here, notice how there isn't a jumble of connections. There's just one line. That reduces a ton of communication. And then this data, it's kept in memory. Okay, so it's the same node all over to the end. And the edges, as long as they fit in memory, so if the entire web happened to fit in 100 gigs, which at some point it did, you could have just kept it all in memory and done your computations and iterations way faster. There was no need to read and write to disk in the middle. So this is all of PageRank code. Okay, so you can even go one step further and get the partitioning a little. So this communication can be optimized as well if you partition such that URLs that have the same domain are on the same machine. And that's reasonable because, first, links are usually inside domains, and then if that's the case, when you're doing the contribution, you don't need to go talk to another machine to do it. So this is another case where knowing the partitioning and being able to inject expert knowledge into the partitioning brings down your computation time. So that's what I mean here by Spark plus controlled partitioning. So regular MapReduce iterations will take a lot of time. This is just for one iteration. And then basic Spark without the partitioning that I mentioned, and then the fancy partitioning. Not fancy. I mean, it's not fancy at all. It's very common. It's very easy. Just a second. Let me get to the next. Okay. So another example that is, so this is currently in Spark. Another example is alternating least squares. So for recommender systems, very often you would like to factorize the matrix into 2 matrices, and then so let's say this is a matrix of users and movies, and you'd like to say have an estimate of a score for a movie that the user hasn't seen. So what's going to happen is that you'll get a vector of length k for the users, and they'll be in the rows of this matrix, and then you'll have a vector for each movie, and they'll be over here in the column, or they're going to be actually in the rows of B and in the columns of B transpose. And then when you need to figure out what the rating for a particular movie is, you dot product the users row with the movies row, and you get a score. And so you need to build this matrix factorization. You assume that there are only k things in the world that k dimensions that affect a user's preference for movies, and then you'd like to learn these 2 matrices so that later you can rate movies. There are many ways to do this. An SVD is one. Another one is alternating least squares. Alternating least squares will take the 2 matrices, start with 2 guesses for A and B, and then so this optimization problem without in general is very hard to do. But if you looking for a local optimum, then it's very easy to do. And to do that, you simply optimize half the parameters at a time. Not half, 1 matrix at a time. If you fix 1 matrix, you can with almost an analytical solution, solve for the other one. So you do this repeatedly. You solve one and then the other a few times, and then you'll have convergence to a local minimum. And to do this, you would have to be a little bit clever, but again, not too clever. You cache two copies of the residual matrix, which is the matrix of ratings that you have. Not the residual matrix, the matrix of ratings. One partition by rows, the other partition by columns, and then that will let you do this update. The update to minimize both of these updates are almost analytical for when you have for the case where you have both cached by row, so you both cached by row and by column. So you end up with two copies of the data in memory, but as a result, you can do something that would take a lot more time on MapReduce very efficiently. So there's a question about how did you compare with GraphLab, and yes, we did. But so GraphLab is on this is on a single machine that's highly optimized, and then this is on a node that has the cluster together has the same specs as that single node. So we can't expect to do as well as the single machine that's beefed up and much more expensive, but we hope to get close, and we do indeed. And then MapReduce is a lot. Yeah. So there was a question.
So I was going to ask that like all these performance results that you're showing. That you're showing for say SVDPC or whatever the
I haven't shown you any results for
I
SVD.
mean, I'm saying that in general. You were showing the performance between Hadoop and Spark.
Yes.
Where Hadoop will always be repeated because of the obvious reason that there is a lot of distances. But when you...
Well, Hadoop has been around for a lot longer, too.
Yeah. But what I'm trying to say is, have you ever done any performance analysis with... you have started the talk by being very critical about MPI. That saying that it's difficult to manage and all these things, like the channels are difficult to create, communications are expensive. But have you done any performance analysis where you compare to Spark and MPI?
Yes. So I don't have them available in this talk, but for example, for ADMM, which is a method of convex optimization, we had an implementation with MPI for logistic regression. And we implemented it in Spark, and we had identical performance. But that's I can see why that happened. It's because there's
on the programmer, right? Like
absolutely.
How well they are writing the code, right?
So we wrote both.
Okay.
We wrote both, and we're good at ADMM and we're good at MPI. The code, the MPI code, was written by some of Stephen Boy's students, who's the creator of ADMM, before he even knew about Spark. And then I had a student build ADMM on top of Spark a month ago, and we compared.
Also has a lot of MPI codes.
So let me continue. It's not the case that Spark will beat MPI every time. Absolutely not. I mean, you're going to get down to the metal with MPI, but you have to do more work too. It's just that's for sure the case. I'm not going to claim that MPI is going to be beaten by Spark, hands down. Absolutely not. You can put all the time, as long as you put enough time into MPI, you'll beat Spark. But you don't want to do that. I mean, if you do that for some very specific applications, please open source your code and make it easy to use for other people. But it will be for that application.
Thanks.
Yeah. Yes.
In the previous slide, actually, how do you partition the matrix by columns instead of by rows?
You do a group by columns, and then you'll have an RDD that has it by columns. If your it depends on how your data came to you. If your data came to you such that it was split row by row, which it usually is, a lot of matrices come in, so then you have to rejig the data around so that you have it column by column. But if your data is already available column by column, you don't need to do that. But that's not going to happen, right? So you do need to. Maybe you might have to do one pass over the data to then have it available keyed by column. That's not, Depends on how your data is coming to you. Okay? So coming back to the MPI question, one of the benefits over MPI and is that you have everything in the same place, right? So you can read your data from a distributed file system. You can, and you know, MPI, you can do MPI on top of HDFS, but yeah, you can do MPI on top of HDFS. So that would it's taken care of for you. But with one line, you can read from HDFS, parse. You have the full programming language at your disposal, but of course you have that with MPI as well. You train and do your queries all in the shell, all in a REPL that is available at your fingertips without having to compile, without having to wait for code to be, without having to wait too long for code to be shipped. Code still does need to be shipped, but it's done. It's done for you. Oh, another benefit over MPI is that you don't need to take care of the master-slave relationship, right? So with MPI, you need to know exactly what code is being written on every single machine, and then they need to communicate together harmoniously. But that goes into just you have to have MPI guts to do MPI. And so this is all available to you, and you know, in a few lines you get almost the full power of your cluster. Okay. So let me tell you about what's going to happen later. So all of what we've talked about right now is what's available, and let's see what's going to come. So the Spark community is very active. It's on GitHub, so you can go and check out the code and play with it as you like, and contributions are very much welcome. We're now we have more contributors than Hadoop does. There are a lot of companies using it, and Yahoo has 1,200 nodes running Spark. So there's a lot of adoption, and the number of you here, or the number of people who signed up is a testament to that. What's currently available, so MLlib is the machine learning part of Spark. It's the part that I most actively work on, and it currently has a large suite of algorithms at your disposal. This suite increased in number with Spark 1.0, which just came out around a month ago. It has all the standard classifiers. It has it has regression and some matrix factorizations. We're working on more of these. It currently has tall and skinny SVD and PCA. We will definitely make that into square SVD, clustering and optimization at a basic level. So all of these we're going to improve on all dimensions there. So currently, we're missing multi-class decision trees. We'll put that in. There's going to be a whole stats library, so all kinds of sampling that you might have to do yourself. Right now, you don't want to code up yourself. Will be available in the stats lib. ADMM, as I mentioned, for general convex optimization, so that if you want to take some application from scientific computing or whatever have you. I mean, a lot of us here are web people. And there's a whole world of engineering outside of the web that uses high-performance computing. And they're slowly now getting on to using commodity clusters, and they're going to be very interested in things like optimization. So I have people working with me on optimizing power grids and placing windmills correctly. And these sorts of things are perhaps less interesting to an audience that is web focused, but these tools are being now used outside of the internet space. LDA is coming. We only started MLlib in September 2013, and already we've had 40 different contributors. If you're in any way interested in machine learning, please come to the mailing list, and we'll be happy to either answer your question or take any contributions you might have. So one particularly interesting application that I'm working on right now is having square SVD be available on Spark. So there is a very mature package from the 70s that does eigenvalue compositions for you, and actually a lot of the eigenvalue compositions that you run eventually get down to Fortran code that was written in the 70s. You might not know that, but MATLAB and some parts of NumPy actually do that. So we took that package and we'd like to distribute it. And one, we could do that. Why? Because all it needed was a matrix vector multiply. So it does all of its work to get eigenvalue combinations by matrix vector multiplies and Yarnall iteration. The matrix vector multiply can be distributed by Spark. So we did that, and then the rest of it, and then someone came along and made JNI interface for this Python, for this Fortran code. And so it's available via Java. Java is available via Scala. We can distribute Scala. So now we have distributed eigenvalue decompositions and singular value decompositions for square matrices. The review, it's currently, it's not in Spark 1. It will be in Spark 1.1. And in general, distributed matrix vector multiplies are something that's very useful. You can do it. PageRank is repeated matrix vector multiplies. Many things can boil down to optimization can be boiled down to solving linear systems, solving least squares, and matrix vector multiplies. And so we'll have that as well. We're taking some very popular software called CVX, which will take your optimization problem that is expressed as text. So you just say, minimize this function. So minimize the square of something. And subject to these constraints, do that for me, please. I don't want to calculate the derivative. I don't want to know whether this function, just do it. So there's a MATLAB package that does this for you. It doesn't distribute. But it turns out that conic optimization, so it's a little bit of a misnomer to put convex optimization in there. Most people, when they say convex optimization, they mean conic optimization. So conic optimization can boil down to nonlinear conjugate gradient, which to solve only needs matrix vector multiplies. And so we can distribute matrix vector multiplies, so let's do that. So we're taking this package called CVX-Pi, which is the Python version of CVX, which is available in MATLAB and used by people who do electrical grid optimization and things like that web companies don't do. And we're distributing that, right? So hopefully you can just give your data. And, well, not hopefully, it's happening. But I can't promise this for 1.1, maybe a little late. And so the key there is that we have distribution in Python. Okay? Spark R is available for R. You can handle RDDs in R. GraphX lets you do a lot of different graph operations with Spark. So you just give Spark a bunch of nodes and edges, and it will do PageRank, connected components, some random walks. We're going to have, GraphX is actually fairly mature now. This is already available. Spark R is also. ML pipelines, so that you don't have to massage your data too much yourself, is coming. It's already pretty easy, but some of the pipelining can be improved. So we're doing this, and then all kinds of applications, as I mentioned. So Spark started out in the Berkeley Amp Lab. I'm building out a lot of support, and I'm getting a lot of support from Stanford. Matej Zaharia, who is the creator of Spark and is an assistant professor at MIT, will bring expertise from MIT. So we're going to have, if not, we already have the expertise of much of the world's computer science that are helping us, and we'd love for you to help us too. It all started out as research, and there's a heavy amount of research still to be done. So it's still very much a hot topic in university campuses. So yeah, please think of Spark whenever you have a big amount of data to go through. Yes, question.
So GPUs are an obvious place where people use data flow. Can you say something about whether or not you've thought about trying to make this usable in heterogeneous computing environment, GPUs as well? The modern ones are quite capable.
Yeah, so CUDA is actually, so a lot of numerical computation does actually happen on CUDA, NVIDIA's data flow model. To be honest, I don't have direct comparisons for you right now. I know there are some, but I don't have them on my mind. So we can take that question offline, and I can point you to the right place to find it. So, yeah. Question?
Yeah, you don't mention the contrib area for...
The what?
The contrib area for Spark.
The contrib area.
Yeah. There's an area on the website where you can actually contribute.
Oh yeah, of course. GitHub pull requests. Please send them.
Okay. But I was wondering if you were going to do it, if they were doing anything with Dempster shaper theory.
I don't know the answer to that. I'm sorry. Yes, question.
You gave a very good talk. I don't know a whole lot of things, so if I ask a stupid question, please forgive me.
That's absolutely fine. Please.
But question number one I have is in Spark, because it's running in memory, and RDDs sort of, very much are dependent on in memory. Other than the fact that it is in memory and therefore very much saving the I/O, what is the advantage of using Spark? If say,
Okay, so let me change it back up a little. It's not the case that RDDs have to be in memory. They'll scroll to disk. Okay.
But the whole advantage of RDDs comes because they're in memory, and you can have lineage, and you can have deep, fault protection.
No, it's not the case that when you're spilling, you're suddenly going to be as good as, say, MapReduce. Even then, the partitioning and the fact that you're not going to have to, for communication between iterations, or for communication between iterations, you can get away with saving a lot by just not writing the disk and keeping even the spilled data on the same node, because then it won't have to be communicated.
But for machine,
and then there's more.
Yeah.
You have a full programming language at your disposal. You're not, and then you're not restricted to maps and reduces. You have a full range of operations at your disposal. Some of the operations are things that are only available in MPI world, for example, on all reduce. So you have a lot more operations. I mean, I could have filled a slide with the operations in addition to map and reduce that you can do. So you have a full programming language, you have a whole lot of more operations, and you have memory usage when possible, you have better communication, less communication when possible.
And the second question, because you said you were very much in machine learning,
yes,
and you described SVDs, SVMs, and ALSs and other functions.
Mm-hmm.
Right? They essentially get loaded so that you can act on RDDs, correct? Meaning those functions have to be, for instance, gradient descent, right? It's a loss function. And for each data, you calculate the gradient function. And you come to a point and you say, this is a loss function. Then you go to the next loss function. Then you go to the next one until you have come to a point there is no improvement in the loss function. Sure. Now, is that part of MLlib live? MLlib?
Oh yeah. MLlib will just take data from you and give you a classifier. Yes.
So, what are the negative points of Spark?
The bindings. I would really like to not have to come up here and tell you that that we have to put in bindings for everything. So I would like to be able to automatically take whatever we have in Scala and instantaneously have it be available in Python and all the other languages that we support. I would like to have, all the ongoing work is missing, and there's a whole slew of machine learning libraries that's missing. There's a ton of stuff that can be made better, and I'm not gonna, So just these are two examples, and I can give you more, but it's probably not the best use of time. Yes.
What time frame would you estimate?
Oh, sorry.
What time frame would you estimate when all these would like to have features be available?
The ones that I mentioned, most of these are slated for 1.1, which is in the next month or two. There are a lot that I didn't mention, and those are further out. Sorry, yes, question.
So we are very excited about Spark. So my whole team now is writing code in Spark.
Wonderful.
What we found is when we write code runs on single machine, when we port it to cluster, it fails. and we don't know why it fails, where it fails. And we couldn't find support on Spark on the Apache website. We searched on the internet, we couldn't, because it's so new.
So the best area for support are the mailing lists.
Yeah, but that will take time, right?
Sorry?
Are we going to get a response within a day or waiting for some people?
So there's mailing list support. So if you put your question up, usually it's answered within a day. I mean, if you look at the mailing lists, it's not a promise or a guarantee in any way. It's completely volunteer run right now. Okay. So people are very active on the mailing lists. There are a lot of questions, and usually questions are resolved there. Now there are other there are distributions that of Cloudera and MapR and so on that have Spark in them, and they have some support as well. So they have more sort of will get to you within a day guarantee type of stuff. I'm not actually a business person, so I don't know the kinds of deals that are there. But
there's also the bug list.
There are many lists that you can get free help on. That's probably where you want to try first.
So are you going to make the mailing list answer question QA available on the web so that people can search for it?
I mean, if you subscribe to them, you'll have them. I believe they're already archived, and you can. Yeah, I believe that's already the case.
Yeah, I think to answer your question,
yeah, you need
that these people are developing it open source, and so you don't get the same kind of support that you're going to get from like Oracle or Cloudera, or if you want that type of support, then you go with like Cloudera, and they're going to give you their distribution, they're going to give you their support and their maintenance, where you can contact them.
So Spark is an open source. Open source, right? Because we like Spark, it's open source. We don't want the cost of going with company.
Well, I mean, it's volunteer run, and so you really have to be nice to the volunteers on the mailing list to get help, right? So that's it. Yeah. Okay. Thanks.